All right, so what I did was I ended up just cropping the other video just to split this up into three parts instead of two, so it made it a little bit more manageable. So this part's just going to be about the neutralization reactions and titrations. So we're actually going to do titrations in class and kind of work with this idea of neutralizing acids with bases, vice versa. So when we have these neutralization reactions occur, it does result in two products. One of those products is what we call a salt. This is just an ionic compound that forms. And of course, water. Now, these are double replacement reactions, so we do have just a swapping of the initial ions, so to speak. But the neutralization should result in a pH that is relatively close to 7, which is neutral. So when we're looking at these reactions, we have our initial ions swapping places. And it doesn't matter what order you put these products in. I usually do the salt first. The salt is going to be the positive ion, the cation there, which is potassium here, and the anion there, which is chlorine, and that is going to be aqueous. So that's our ionic salt and water. All right. So those are, that's pretty much our template for these. So these are just straight up double replacement reactions forming an ionic salt. So in this case, this is NaNO3 and water. And again, remember, we usually can write water as HOH with that hydrogen in the front coming together with that hydroxide ion in the back as well. Let's go through this one. Now notice we have, it's a little bit different here because we have two hydroxides because that magnesium has a positive 2 charge. And when it's going to pair up with this chlorate ion, we end up having to balance out those charges. So, yep, you have to remember that you have to balance all the charges. And, of course, balance your equations when necessary. So we put a 2 here, which is going to cause us to put a 2 there as well. Over here, the hydrogen is going to swap with the barium. Barium has a +2 charge. The phosphate group that it's going to end up with has a -3, so we have a 3PO4 2. It is aqueous. The salt will be aqueous because it will be dissolved in solution, plus H2O. That's not a 2, that's a 2. And of course, balancing leads us to, I need a 3 in front there. I need 6 OHs, which means I also need 6 H's there. We should be good there. And then, of course, we have calcium with our sulfate here. That's a AQ. Going a little too quick. And water. So, again, the same idea. Salt, ionic compound, right? Plus water. And I like balancing, so we balance. We end up needing a 2 out front there, and we are good. So those are just our neutralization reactions. And what happens in neutralization reactions, again, is that we are trying to even out the moles of acid and moles of base. So that's what we call an equivalence point. All right, and at this equivalence point, the moles of that acid should equal the moles of the base. And because we're talking about concentrations and amounts of liquids that we use volume to measure, we actually have this relationship from one of our earlier units where molarity, which is the concentration, is equal to the moles of a substance divided by the volume, right? Noting that the volume is in liters, right? But you can then rearrange this equation to then use molarity and volume measurements that will be given to then equate that to the mole. And depending upon what you're talking about, either the molarity of the acid or the base, the volume of the acid or the base, you're able to get the moles of acid or base. So that's kind of what I outline here, where the molarity of the acid times the volume of the acid is going to be equivalent to the moles of acid that we have. Same thing for the base on the other side. Again, remember that volume should be in liters when we're talking about molarity. Volume should be in liters, right? So may have to do some conversions. And one last thing, because some of our acids are polyprotic, which means there's multiple ions or multiple hydrogen ions, kind of like you see right there in that first example problem down below. And because some of our bases they are paired up with something that has a charge other than a +1 at some times, we actually have to identify how many of those ions for each side would be created, and that's what these ends are right here. All right, so you see how we've kind of just added that in, and we can do this with stoichiometry as well, but it's kind of like a little shortcut. It's a little bit easier to just identify when those things are dissolved in solution and dissociated. They're going to create the number of ions that they are made up of, right? And that's the idea behind that. So we're actually able to grab that value there and then figure out what that N value is. So the NH, the number of those hydrogen ions there, and not to confuse, I won't start putting in the ion charge there. We kind of know that an H is a +1, but this would be a 2 there because there's 2 hydrogens that'll be created from the diprotic, we say, is 2 acid, that's sulfuric acid there. So then we go through and we say, okay, well, how many, what do we have here? Well, hydrochloric acid, it just has 1, right? So that is our hydrogen ion count. We do the same thing here. That's a 3, right? And we do the same thing over here based on the OH ion amount. So NOH is going to be 1. In this case, it will be 2. And in this case, it will be 3. So that's just another wrinkle that we have that we add to our titration equation, as we'll call it. So let's look at an example of how this is put into practice. So we have these solutions, and what we're going to do is we're going to take whatever information we're provided. As we can see, we can set up all of our givens and our unknowns, right? And if you want, you can add the ends there. I choose not to because we can really kind of clearly see it based off of the formula that's given. Don't really have to write it out, but you can if you want. So let's just put in what we know. I know that this is my acid because that's in H in the front, right? That means that there's a hydrogen ion there. And then this is my base, right? Because there's the OH in the end, the hydroxide ion is a part of that. So I have my acid and my base information, so I'm going to just plug it in. The molarity of the acid is 0.1 molar. The volume of the acid, remember, that is 50 milliliters. However, we need to make sure that it is in liters, so we convert that very quickly. Right, do the three decimal places back, divide by 1,000, same thing, and we get 0.050 liters. So there's 0.050 liters of that solution. We're looking for the volume in liters. That's what we do not know. And of course, we know that the molarity of the basic solution, the sodium hydroxide, is 0.25 molar. So if you want, you can say the number of hydrogen ions and the number of hydroxide ions for each are going to be 1. And again, it's just based off of how many are a part of those formulas there. So then here's our equation, right? The acid side and our base side. And not quite symmetrical, but I just put the ends on each end. It doesn't really matter where they are. We're multiplying here. And then I plug in. The molarity of the acid was 0.1. The volume is 0.050, right? The molarity of the base, 0.25. Volume of the base, we do not know. We also know that there's a value of 1 there. So when you are going through your calculations, take 1 times 0.1 times 0.05, and we end up with 0.005 on the acid side. And of course, this is just going to be 0.25 times volume of the base there. Divide by 0.25 on both sides. And the volume of the base that we end up with is going to be our 0.005 divided by 0.25. And we end up with about 0.2 liters of our base that we have, that we would need to neutralize that amount of acid in that, or with that concentration, right? So again, note that my answer is going to be in liters because we converted to liters before. You have to, right, when we were using molarity. Let's try this next one here. So we have, we can label all of our information, right? Givens, unknowns. Well, unknown, right? There's only going to be one unknown for all of us. Making sure that we are converting milliliters when applicable. And now that is the volume for a base. Why do I know that? Well, because I see that the substance that I'm provided there is the barium hydroxide. Hydroxide is a base, so this is going to turn into 0.0274 liters. The molarity of that is 0.0154 molar. The volume of the acid we are provided, again, milliliters needs to become liters, so that would be 0.020 liters. And we are looking for the molarity of the acid in this case. The number of hydrogen ions is going to be 1 based on that 1 hydrogen there in the hydrochloric acid. And the number of hydroxide ions is going to be 2 in this case because of the number of hydroxide ions that are, a part of the barium hydroxide. So when we go in, we are going to, that's not an N, MA VA equals MB VB NOH. Right? You could say NB too if you want, really. But as long as you know which side is which, it really doesn't matter. 1, we do not know the molarity of the acid. We do know the volume of the acid, 0.02. And then we have the molarity of the base, which is 0.0154. The volume of the base is 0.0274. And the number of hydroxide ions that will be formed in solution is 2. All right, so this side's easy to simplify. 1 times 0.02. That is just going to be 0.02. And 0.0154 times 0.0274 times 2 is going to give us 8.4. We'll round that up. You're not supposed to round too soon, but it's okay. That's a 9. 0.44 times 10 to the negative 4th there. All right, of course, that's what that operation in the calculator represents. So divide through by 0.02. that rhymed, and I did not mean for it to do so. And then we just take that value. So just to be sure that the calculator knows what I'm doing, I am going to take any scientific notation value and put it in parentheses, and then I'm going to divide it by the 0.02, and that's going to give me a molarity of my acid of about 0.0422. Of course, that's molar, and doesn't matter how many decimal places you go to. You know, we don't do sig figs necessarily here, but you know, if there's only 3 whole numbers that aren't 0, you know, after, then I would add them all. You could make this 0.042 if you wanted. So I'm not going to be too much of a stickler on that. And last but not least, let's do this last one, MAVAMB VB. Titration reveals that much 3 molar H2SO4, sulfuric acid, is required to neutralize that much sodium hydroxide solution. So again, anytime I see milliliters, I'm just going to move that decimal place backward 3 times, or divide by 1,000. So the volume of the acid, I know this is an acid because of those hydrogens in front, and I know this is a base because of the hydroxide ions in the back. The molarity is 3 molar. The volume is 0.0116 liters, required to neutralize 0.025 liters of base, and that is a volume, not a molarity, because we're looking for the molarity. And there we go. And number of hydrogen ions, number of hydroxide ions. For the hydrogen ions, there will be 2 based on how many hydrogen are part of the sulfuric acid solution. And then, of course, there's only going to be 1 hydroxide because of the 1 hydroxide ion there. NHMAVA equals MBVB and NOH. We have 2. We have, we know that molarity, that is 3. Volume of the acid, 0.0116 equals, we do not know the molarity of the base here that we are neutralizing. The volume of the base we know is 0.025 and 1. All right, so this side, 2 times 3 times 0.0116. Says 0.0696, and this side is going to be molarity of the base is equal to 0.025. All right, divide by 0.025 on both sides, and the molarity of the base that we have neutralized is 2.784 molar. All right, so these are just a couple of examples. For my class, these will go off of 11.05 for our assignment. So if you have any questions, just always feel free to let me know.